Good morning, ladies and gentlemen. Good morning, ladies and gentlemen, and welcome to this webinar on LDACS for the L-band Digital Aeronautical Communication System. My name is Jackie Pouzet. I'm leading the communication and frequency coordination activities at Eurocontrol in Brussels. And I'm pleased to have together with us today eminent panel members to talk about LDACS. So I will introduce the panel members in a minute. But the purpose of the webinar is basically the first of a series of several webinars talking about the future of aviation in terms of communication, mainly regarding the digitalization. Air traffic control is requiring more air-ground mobile secure digital communications. And the way we are foreseeing the future is that we will have more and more machine-to-machine communications instead of human-to-human communications. Hence, we need a performance air-ground communication system. This is not new. This need was identified by ICAO about 10 years ago. And some of the members, panel members that are here today, we recall the story that has been done during the past years, some action plans that have been put in place. In the meantime, the mobile technology has evolved, and it has been developed, amongst others, in Europe by SESAR. We do have some speakers from the SESAR joint undertaking that has been developed together in conjunction with ICAO. The time for implementation decision is coming. So consequently, in Europe, we have the Network Director of Technology, a group called NDTech, that is working in close relationship with the joint CNS stakeholder platform, which is a group co-chaired by EASA and Eurocontrol, that have given us a task to develop a business case for the new air-ground technology implementations. So there are several options. LDACS is just one of the potential options. There are other potential technology like SATCOM technology, like other VHF technology. But basically, the feedback we've got from our stakeholders is what is LDACS? So that's the purpose of this webinar, is to, let's say, basically present you what is LDACS. So the objective of this webinar is to increase the awareness of the LDACS technology. So it doesn't mean that LDACS is selected in Europe for implementation. It's just one of the options. I insist on this point. But it's important that everybody is aware of what are the performances and what we can do with LDACS. So consequently, we are organizing together with the SGU, the SESAR joint undertaking, a series of 4 webinars. Together with a panel of experts from different organizations. Today we are going to have SGU, IATA, ICAO, and FAA. But later on, other seminars will be organized with other partners coming from industry, air navigation service providers, research centers and laboratories, airspace users, communication service providers, and so on. So basically, we have foreseen a series of 4 webinars. The first one, which is this one, a general introduction to LDACS, and I have the pleasure to moderate this seminar today. Then the second one, which will be the most interesting one for those who want to have all the details of LDACS. So the second one will provide technical details and capability of LDACS for communication and integrated CNS, because this technology has also the capability of provide navigation and surveillance services. So this one is supposed to take place the 2nd of June. So please put this date in the agenda, same timing as today. Then we are going to have other stakeholders that will speak about potential deployment options and what could be some transition scenario. We are foreseeing this webinar for end of June or beginning of July. And the last one, with economic and business consideration for all stakeholders, is supposed to take place in September. We expect to come back with some feedback to our director by end of this year regarding a potential decision on the future evolution of the air-ground communication infrastructure in Europe. So today, as I said, for the general introduction to LDACS, we are going to have eminent panel members. I will introduce them, one of them at the beginning of the presentation. The first one to speak will be Vaughan Mayola from ICAO. Then we will have some colleagues from IATA, Nopodol Pringbanic, Brian Philippe from FAA, and Ruben Flor from the SGU. At Eurocontrol, we will moderate this webinar. So I'm here together in Brussels with Philippe Sacré, that has been heavily involved in LDACS development, and that will help me to collect all the questions you may have during this webinar. So the agenda for this first session, the first one, we are going to have ICAO, we introduce the motivation for LDACS. Then IATA and NOPADOL, we introduce a key consideration for future AOC ATC communications. We will have the SESAR R&D perspective by Ruben Flor. FAA Next Gen perspective, and Brent Phillips will recall the story on the future communication infrastructure. And then Vaughan Mayola from IATA will come back to tell us where we are with LDACS standardization. So regarding your session, you cannot speak during the session because all the mics are mute. We have a lot of participants today. So, but please do not hesitate to use the question via the tab that you have, but use the question tab instead of the chat. It's better for us to collect all the questions. And then we will try to collect the question and raise the question to the panel members after. So that's the end for the introduction today. I will pass the floor now to Vaughan. So Vaughan Mayola has worked for almost 40 years in the field of aviation communication. Prior to joining ICAO, he held various roles with communication service providers, CITA and Austrian Civil Aviation Authority. He currently serves as secretary of the ICAO communication panels. So Vaughan, the floor is yours.
Yes, thank you, Jackie, and a warm welcome to all of today's participants, and I see we have a great number of them. For my part today, I'd like to provide a brief introduction to LDACS, LDACS being the L-band Digital Aviation Communication System. Specifically, I'd like to talk about the motivation for LDACS, and to introduce that, I'd just like to give a brief outline for this morning's or this afternoon's presentation, depending on where you are. With regard to the motivation for LDACS, the real question we'd like to answer is, why do we need it, and why do we think it is the solution to our problems? Then, once we've done that, we'll have a brief description of LDACS in terms of both its basic functionality, but something that I find very exciting, the fact that it's got what we call extended functionality. The LDACS system can actually perform a number of roles in addition to communication, and I'll come to that in later slides. Thank you. So, motivation. Why do we need LDACS? Well, from the beginning of modern civilization until today, the main medium for communication has been analog voice, specifically digital sideband AM modulation. That's AM, not even FM. Now, many years ago, back in the 1980s, something known as the FANS Committee, Future Air Navigation Systems Committee, which was an ad hoc committee of ICAO, sat down and developed a concept for future civil aviation, or future air traffic management to be specific. And what they envisaged was a shift from the analog voice communications to a future where we were dependent on digital communications. In other words, they could anticipate the developments that were coming in just general telecoms to begin with. Now, their future concept was based on the shift from voice to digital communications, with voice being available, of course, for non-routine and emergency communications. And this new concept will be underpinned by the use of satellite technology, basically satellite navigation and, of course, satellite communications. Satellite communications would really be the global enabler for future communications because it does have global coverage and it can provide service where traditional terrestrial means cannot. Now, those concepts have been advanced, developed, matured by various other parties within the civil aviation community. We're now talking about future concepts such as 4D trajectory. We're talking about the aircraft being a node on what's known as the SWIM network, System-Wide Information Management, where the aircraft will have full access to all sorts of aeronautical information services. These things will call for a high-speed broadband capability. We don't have it today. Unfortunately, although we have made some good progress, with the shift from voice to digital communications. We've somewhat stalled, and let me explain. We've made use of digital communications for air traffic management for over 20 years now. The first implementation of that was what's known as the FANS package, or FANS 1A. And that's been used to do some fairly elegant things for 20 years now. Route clearances have been delivered in the Pacific, on the North Atlantic, and over continental Europe. Data link is now used today to routinely deliver clearances and perform a number of routine functions such as position reporting. In Europe, specifically, they're not using FANS so much as something known as ATM Baseline 1. But nonetheless, though, these systems still can't deliver on the final promise. They were a great start, and they allowed us to take that big, brave leap into the world of digital ATM. But the capability we have today, based on technologies such as VDL Mode 2, provides nothing better than a basic SMS type service. In other words, very short messages, infrequently sent. And when I say a basic SMS services, we don't even have the emojis and graphics and moving GIFs that you can get on your cell phone today. They're just not possible with the existing systems. They've also got very limited capacity as well. So until we have something better, until we have a future broadband data link, we really can't deliver on the concept that was envisaged. You know, we won't be able to support 4D trajectory, SWIM, dynamic RMP, and these other advanced ATM concepts that are being developed today. Unfortunately, the limit is there. The current technology cannot support it. We need something new. That something new is LDACS. Just recapping what was said in the past few minutes, ATM is modernising. We're moving to new concepts, and we're really going to see a paradigm change. I've mentioned trajectory-based operations, the shift from voice to data. The aircraft will really be integrated into a global data network and via another upcoming development known as SWIM. SWIM is interesting, and it's based on the latest techniques. It's based on what they call XML, which is extensible markup language. What is that? Well, that's the method used to encode web pages. The web pages we see today with full colour graphics, audio visuals, this sort of thing. Again, the current communication systems cannot support those. Now, that brings to mind another fact. Graphics to the cockpit will be a reality in the future. If you read the trade journals, you see constant references to something called the connected aircraft. For us in ATM, air traffic management, that means the connected cockpit. So there is clearly an emerging demand for a broadband data link technology, and we need to start working on one now, and we have, the result being LDACS. We also face a number of other challenges. Air traffic is increasing at a rate of roughly 6% per annum. Admittedly, with the COVID-19 pandemic, we're in the middle of a dramatic slowdown, but we're confident that we will see a return to growth in the future. Many regions of the world were experiencing air traffic growth of the order of 6% per annum. That's a doubling every 12 years, and then another doubling 12 years after that. Again, the current communications infrastructure simply cannot handle that growth. So what we need is not just a new digital system to carry us into the future. We need a system that's future-proof, one that's scalable and that can accommodate the growth that we're seeing. As well as that, we need to be spectrum efficient. Why is that? Aviation has for many decades enjoyed the benefit of a lot of dedicated, protected, what we call aeronautical spectrum. However, that spectrum occupies a number of sweet spots among the radio bands. Many of the services we support today for communication, navigation, surveillance use frequencies which are ideal. They represent the sweet spot for mobile communications. And the mobile phone industry has been eyeing that greedily for a long, long time. In other words, the sharks are circling. There are other sectors of the economy who would really like to get their hands on our radio spectrum, so we need to protect it. It's not to say we might lose this spectrum, but we certainly will not be getting any more. And yet we have to accommodate all of this growth, both in air traffic and in the sophistication of the applications we provide. That is going to be a challenge. So not only do we need a broadband data link, we need a spectrum efficient broadband data link. What other issues do we face, which we think LDACS can help us resolve? Security will be a big one. As Jackie said in his introduction, the future concepts will be relying more and more on automation. We'll be seeing machine-to-machine type communication. And bear in mind that when it comes to cybersecurity, it's not pilots and controllers that get hacked, it's the systems that they use, and we need to protect those systems. The good thing is that LDACS has such security built into it. It's a basic capability. Excuse me. Now, there is one other problem we need to confront, and that is that the addition of security adds to the data burden. An encrypted message is typically twice as big as a non-encrypted message. We need the capacity to support that. Again, LDACS gives us that. The other good thing about it is that there was something, as part of the original FANS concept, something called the Future Communications Infrastructure was developed. And what that meant was that we would have a number of different communication technologies available at any given time to support services in all manner of airspace under all operating conditions. Regardless of how you look at that, LDACS is likely to be a main component of that future communications infrastructure. And another good thing about LDACS is that it's multifunctional. It can perform a number of other roles in addition to its primary role as a communications medium. But we'll talk about that more a little bit later, and that will be covered in more detail by some of the later speakers. Again, this slide was also part of Jackie's introduction, and it basically shows the anticipated future communication infrastructure where multiple links are available, both satellite as a complement to terrestrial medium, satellite as a primary medium in remote and oceanic airspace. And another thing I should have mentioned is that LDACS also has the capability to provide air-to-air communications. We do that today with 1090, 1030 squitters, but they're very limited, a little bit like our SMS system that I talked about earlier. LDACS will provide something better. So let's have a brief description of LDACS. As mentioned, it's the L-band digital aeronautical communication system. Why L-band? Well, presently today, the majority of aeronautical telecommunication, both airline and ATC communication, takes place in some 18 megahertz of spectrum in the VHF band. That is very congested. It's exhausted at this point. There are no more frequencies to be given out, and it has caused problems with our first attempts at digital communications. Most of Europe was supported by just one frequency for VDL Mode 2. That has been enhanced and they've reaped the benefits. But many continent-wide areas have data links serviced by just one frequency. We've got to move on from that if we're to accommodate the increased growth, the advanced applications and so forth. One obvious way of doing that is to get out of the VHF band, move to the L band, which is what we're anticipating with LDACS. LDACS, as mentioned, is a broadband system. It's based on something called orthogonal frequency division multiplexing, or OFDM. Oh, again, I won't go into the details. I couldn't do them justice. But what I can say is that that's the same technology used by our modern mobile phones, be they 3G, 4G, or even 5G. Another reason why it is the method of choice is that it's very resistant to interference. And I think I wouldn't have to work hard to convince you that an airport is an environment that generates a lot of interference. So we need to protect ourselves from that. LDACS can do that. It uses a number of advanced techniques to ensure that it provides high availability communications. The modulation and encoding is adaptive. In other words, it adapts to the transmission conditions that prevail at a given time. And that is to ensure that all traffic will get through uncorrupted. And again, the system is very robust in the face of interference. LDACS will offer a much greater quality of service. We're looking at much faster access times and reduced transit delays. We're talking sub-second type message delivery. And because it will support a range of traffic, from very safety sensitive traffic, clearances upon approach, that sort of thing, to routine traffic, airlines just making sure there are enough wheelchairs at the gate when they land. We have to prioritise that traffic to make sure that the safety sensitive and the critical traffic gets through first. LDACS can support that. LDACS also overcomes a number of the problems of today's systems, one of which is both the forward and reverse link will take place on one frequency. So in other words, you can't transmit and receive at the same time. LDACS can, and it can do it on multiple frequencies. So we're going to see a quantum leap in performance here. Another good thing about LDACS, and this is something I'm really excited by, I mentioned earlier that in many cases, today's data communication systems, or aeronautical data communication systems, are often limited to the use of just one channel for all of the aircraft operating over an entire continent in some cases. LDACS instead works on a cellular structure where each base station on the ground has its own frequency. What that means is that frequencies can be reused. So if we have a channel, a base station here shown in blue, the blue frequency can be reused here and here, and so forth. So in other words, what we can do is we can provide service to a very, very large area with just a handful of frequencies. Not only that, the system is scalable, whether it's a small country or whether it's a continent-sized region. We can still provide a satisfactory service with the same handful of frequencies. So this is a particularly good thing. So we did use the term future-proof before. That is why we see it as being future-proof. Another good thing is that LDACS supports seamless handovers. So as an aircraft flies from one base station to another, there is no need for a manual frequency change, no need for an instruction to change frequencies or anything like that. It will be seamless. And in fact, in the future too, LDACS could be capable of supporting air-to-ground voice. Now, wouldn't that be good if we had that without the need for frequency changes and handovers? Anyway, I will move on. So, which problems does it solve? I've mentioned that it supports all kinds of ATM communications, both ATC, airline operational communications, and also airline administrative communications. They're all essential to the safety and regularity of flight. They have to be catered to by the same standardised high-performance data links that'll help us resolve our capacity problems and accommodate future growth. Now, there will be a transition period where we have VDL Mode 2 and other technologies used in parallel with LDACS. LDACS will, in those cases, will really just be an additional broadband communications channel capable of bringing more services to the cockpit. But the various industry groups working on LDACS are very mindful of the fact that the airlines do not want to have to retrofit or add another box to the avionics bay on the aircraft. They don't want to have to add another antenna to the aircraft. There's already some 36 or more on an aircraft. They don't want to have to punch another hole in the aircraft skin to get cabling to that antenna. So they're looking at and under development are systems and multi-mode systems that can support LDACS and VDL Mode 2 in the same box. There's also work underway to make use of the existing antennas on the aircraft. So actually implementing LDACS on an airframe will involve not much more than simply replacing a box and doing some necessary wiring and cabling. We're not talking about implementing a brand new system here. We're talking about, in practical terms, we'll mean the swap out of the box, some rewiring and recabling, and the capability will be there. The system will be adaptable. So in other words, when LDACS ground infrastructure is in place, the system will switch to LDACS and make use of that. In other regions, it will use the available communications. So we've thought a lot about the transition, and hopefully we'll solve those problems in the near future. So just as a recap, I've mentioned the advanced applications that are forthcoming, 4D trajectories, weather maps being available in the cockpit, integration into the SWIM network and whatever that brings, because that really is treasure trove. That offers a treasure trove of possibilities, as well as that LDACS offers secure communications, and it has the capacity to accommodate all manner of security precautions such as encryption, authentication, and so forth. Extended functionality. LDACS can also support a ranging and navigation capability. What that means is when there's LDACS infrastructure on the ground, it can do position determination, much like GPS. That means it could act as a backup to GPS, should there be interference to GPS or some other problem in a given region. As well as that, that information can also be fed into the fused navigation display and so processing rather, where the input from various nav aids is blended to provide the navigation fix to the flight management system. That will be no problem. LDACS could act as an additional position or navigation aid there. It's also well suited to provide an alternate position navigation and timing system, APNT. That is a part of both the next gen plan and this program in the States. It's part of the European ATM master plan, because they've recognised that GPS is vulnerable and we have a high dependency on it today. You know, we need something as a backup. LDACS, where the infrastructure is available, will be able to do that. LDACS can also support GBAS. It can actually support the data broadcast capability of a VDV with more capacity and less latency. So we did say that LDACS is multifunctional. And it's probably going to be our first example of truly integrated CNS. And that's a concept that's been talked about for a long time, but LDACS will make it possible. So with that, I'll just summarise, saying LDACS is extendable and future-proof. It's very scalable with higher bandwidth, and it can be easily expanded both geographically and in terms of capacity without much difficulty. So it really is a future-proof system. And with that, I'll end and say thank you and hand the floor back to the chairman, Jackie. Over to you, Jackie.
Thank you very much, Vaughan, for this very interesting overview of LDACS. I can see that it is generating already a lot of questions. We will not be in a position to answer all these questions, but we will come back later on, because in the next presentation, you may have to answer to part of the questions. My suggestion is to move on now to the next presenter. So the next presenter will be Mr. Nopadol Pringbanic. He is the Global Head of Air Traffic Management Engineering and Aviation Radio Spectrum for International Air Transport Association, IATA. He is responsible for developing IATA's global policy strategy and airline position relating to CNS, ATM technology and aviation frequency spectrum. Nopadol is the co-chair of the ICAO communication panels and has served as the IATA nominated panel member for numerous ICAO technical panels, including frequency spectrum management. So I think it's very nice to have the view of the airspace users. So Nopadol, the floor is yours.
Thank you very much, Jackie. First of all, can you hear me and can you see my screen?
Yes, we can see the screen and we can hear you very well.
Okay, thank you very much. So good morning, good afternoon, good evening, everyone. It's actually my great pleasure to actually discuss with you some of the key considerations why, when airspace user, for example, the airlines, when we're looking at the future communication infrastructure, what are the key considerations that we need to think about, and we want to make sure that all those elements are in place before we making a very important decisions into the infrastructure and avionic investment into the future. So in this presentation, first, I would go over very quickly what type of communication messages that are being used today. Basically, what is included in the airlines operational communication, AOC, and also we also recognize the importance of ATC communication or ATS communication with, used by air traffic control to communicate with the pilot on board the aircraft. Following the quick overview of the current use of the communication infrastructure, I will look into some of the future applications that airlines are expecting. Some of them are already being initially introduced on board the aircraft already, and some of those applications would highlight and emphasize the need for broadband connectivities and also some of the security requirements that need to be put in place. The key point of this presentation would be in the last two slides, and basically that would capture some of the key considerations that need to be considered by all the stakeholders, including the airlines themselves, when we actually discussing what would be appropriate future communication system as we move forward into the time with broadband connectivities, it actually will become more nominal on board the aircraft. So just a quick couple slides on what is the airline operational communications. You hear this mentioned earlier by Warren that future communication system would need to support both AOC, ATC, and also AAC traffic. So just a quick couple slides that looking at what is airline operational communication and why is it important for airlines operations. Basically, AOC is well supported by both IQ and ITU regulations, and it's required for throughout all phases of flight, and this is something that links directly to the safety and regularities of the flight operations. AOC itself complies with both voice and data, and it's allowed the aircraft to communicate with some of the agency on the ground, which we need to communicate to basically share and also get information so that the safe and efficient flight operation can be conducted. AOC is actually connected not just only to the airline operational control center. Basically, that's where the airline, the pilot is discussed with some of the ground crew, dispatcher, some of the airspace requirement and so on to talk to the airlines operation centers. That's obviously important with itself. But beyond that, the AOC is used to support communication between pilot and ground service organization. This support operations such as ground handling, refueling of aircraft, and also supporting some of the aircraft maintenance activities. Also, quite recently, some of the newer application of AOC is including the sharing of the engine performance data and also engine status data to basically the engine manufacturers and also the maintenance organization. So this slide basically breaks down AOC, the typical AOC messages into basically two big sets. The first set is the uplink message, the type of data that actually sent toward the aircraft. And the second set is the downlink message that looking at another way around the information that the aircraft send out to the ground unit, ground facilities. For the uplink part that you see here, a lot of information is directly related to the flight operations, basically flight planning, some of the route and weather informations, notifications regarding dangerous goods, for example, some of the imminent security information that sometimes need to be sent to the aircraft, and also something that facilitates the passengers connecting to various destinations. So as you see here on the uplink part, a lot of the regularity of flight is dependent and highly dependent on having this information sent reliably to the cockpit and be accessed by the pilot. On the downlink side, a lot of the operational pilot report are often sent out to the AOC. There are also sometimes the engines monitoring data that are sent. And also, as you see here, the flight status information is actually being circulated and be sent out to the downlink message to the airlines operational centers or the ground handling services so that they are ready when the aircraft arrive at the intended destination. What we see prior to COVID-19 is that the level of AOC traffic have grown quite significantly. Of course, that comes naturally by the increased amount of the number of aircraft and also the type of aircraft that is flying. As you see in this slide, on the second bullet point, newer aircraft also sending more data. AOC now being the size of the masses and also the number of the masses is actually increased quite dramatically recently. There are also additional use by the airline for the AOC, for example, to provide a report on specific operations and also specific procedures that airlines are using AOC as a mean for communicating from the cockpit down to the ground operational center. With the use of AOC in support both the safety and the regularity aspect of the flight, of course, AOC require as a communication system. AOC require communication system that provide appropriate quality of service. You cannot really not rely on qualities of communications, both in terms of latency and availability and some other important QoS parameters that need to be guaranteed to make sure that the AOC messages are being transmitted and received quite reliably on board the aircraft and to the ground infrastructure. We also foresee at this time, we also experience at this time some of the issues relating to the VDL frequency overload in Europe in particular, and also some of the problem with the limitations of having only one frequency supporting VSF data link. In addition to AOC, another very, very important and safety critical communications that need to be taken into account is ATC, ATS communications. Basically, these are safety and time critical. So that is reliable. QoS is obviously mandatory. You need to make sure that the masses arrive from the ATC to pilot or from pilot to ATC in a well-structured, well-timed manner. So we know precisely, for example, if ATC would like to ask the aircraft to climb to ensure the separations, that message arrive at the right time to the cockpit, to the pilot, so that the aircraft and the pilot can react accordingly. This type of communication, ATS and ATC communication, is actually used quite routinely in support of aircraft separations, assurance, and also many of other ATM applications. Some of the example of ATS communication is provided here, so I'm not going to walk through it. But one thing I would like to highlight is on the last bullet point, that in the future, the size, and it is actually very foreseeable that the size of the data that it will be sent in support of ATC communication will be increased when we're actually looking at trajectory-based operations and sending aircraft trajectory data to our communication infrastructure. So with ATS messages, safety and time critical. We are also noting that for AOC messages, most of the uplink AOC messages are very essential for safety and regularity of flight. So it's also quite time critical for the uplink side. But one thing we also recognize that some of the downlink AOC messages, for example, the engine maintenance data, while those are important and actually quite essential for the flight operation, but it's less time critical. It can have lower priorities in terms of the transmission of the message as compared to ATS services and ATS messages that actually require to ensure the separation among the aircraft. When we're looking at infrastructure and avionics, currently AOC and ATS are transmitted to the same frequency using the same aircraft equipment. And that's obviously a reason behind that, because both AOC and ATS are using the same infrastructure on board the aircraft. There's a limited space on board for the aircraft to take into account antenna and avionics, and of course, adding another set of avionics onto the aircraft unnecessarily is not welcome for the airlines, both for purpose of the space, but also the weight and the power consumption implication that need to be taken care of. Also, adding another antenna on board the aircraft is not always something that is easy to do. The cost of that can be quite prohibitive, and that is why we actually emphasize the need that for AOC and ATS communications, a shared infrastructure and shared equipment is probably one of the highest consideration that need to be taken into account. But with that said, in the future system, if there is a capability inside the common system to give the right priorities to various messages, that is something that will be highly desirable. Now, looking a little bit into what is coming next. What you see on the screen here is some of the more graphical display on board aircraft and some of the applications that are going to be used to support that and actually start being introduced to some of the airlines now is, for example, a more graphic-oriented electronic flyback. What you see on this screen is the weather map. Basically, that graphic capabilities require higher throughput and higher bandwidth, which actually the current VDL may not be able to support. This is something that requires higher throughput, and we want that to also be reliable. So the quality of service needs to be ensured, and that's highly desirable. Also, if you're looking at the lower pictures in the same screen, more modern aircraft are now well connected, and there's a lot of information that will be sent in and out of the aircraft. The connected cockpit concept is very important moving forward to allow efficiency of flight operations, and we need those data to be communicated. And for that communications to take place appropriately, a proper infrastructure need to be put in place. Also, as you see that some of the information that are now being sent to the cockpit will be interfaced to some of the safety critical equipment on board aircraft, for example, flight management system, the controller, pilot data link communication, CPDLC, my apology for misspelling it there. But with that interface and connected nature into some of the safety critical equipment, cybersecurity issue need to be addressed. This is all paramount important that we have a secure connections toward the aircraft and make sure that we are not create a weakness within the communication network so that it can be attacked by a malintended cybersecurity threat. So the next two slides is basically the key message and the key summaries of these presentations. While I will try to bring together some of the key considerations that when airspace users and airline looking at future communication infrastructure, what need to be in place, what type of consideration that need to be looked at, and if some of the communication infrastructure is be able to check most of these checklists or all of them, of course, they will become a very, very strong candidate. The first one is that we want a communication system that can support both ATS and AOC, common service, common infrastructure, common avionics, for the reason that I mentioned already on the earlier slide. With the new applications coming in, with, for example, the graphic moving weather map or things like connected cockpit concept and electronic flyback, you probably need a higher bandwidth and higher throughput in the communication infrastructure that should be able to support. And also, as airlines actually operate globally, we want a global standardized solution, something that we can rely on in terms of the quality of service, and that the QoS can be enforced to appropriate standard and regulatory framework. Security is important, and the capability to support privatization is also important, and that need to be written and clearly dictated by the standard itself. So we can make sure that it is implemented and is actually supported by the system. We also recognize that in future environment, there may be a need of mixing multiple communication links, for example, terrestrial communication with satellite communications. So the system itself and the interface need to be able to adapt to multi-link environment and work with that correctly. Spectrum issue is also very important, as you mentioned, as Warren from IQ have already mentioned this. Right now, we are facing a lot of spectrum challenges in the global level. So we want the new communication system to be spectrum efficient. And also we need to make sure that it's robust against any potential interference. And that can be done through the combination of technical measures, for example, a stronger interference rejection mask, but also it needs to be part of the legal regulatory protection as well that would come from either ICAO or most likely the ITU radio regulations, so that it provides a proper protections to the investment and a proper protection to the operations of the new system coming forward. Cost is important. Of course, we need to look at a more cost-effective solution, but of course that need to fulfill the operational requirement as well. So there is a balance between having a very good system with very high cost and some of the probably less robust system but cheaper cost that need to be taken into account. So cost effectiveness of the infrastructure and avionics setup and also the service fee would need to be taken into account in the consideration itself. It need to be timely and time appropriate. Aviation as industry at this point in time, we get pretty hard hit by the impact from the financial impact of the COVID-19 pandemic. So we need to see when would be the right time so that we can make a decisions of moving forward with a new, more robust infrastructure. The timing need to be right and it needs to be appropriate by considering the airline's financial situation. So my last slide here is capture another set of consideration, but this one is more focusing on the actual deployment and what need to be part of the deployment plan moving forward. Of course, we want a seamless transition. Airline doesn't stop flying, we fly every day. So we actually need to make sure that the transition from the old capabilities and the old infrastructure into the new infrastructure is well coordinated with a clear migration plan. Need to be developed, that need to be commonly understood, need to be communicated, and it need to be put in place as we move forward. Forward fit approach is always preferred with a clear demonstration of early benefit that would create a national incentive for airlines to move forward with a forward fit approach. I think that is also very important, taking into account that when we invest in certain infrastructure, we expect that to work for the next 15 to 20 years. That's a normal life cycle of avionics on board aircraft. Synchronized deployment is also important to implement any new infrastructure, communication infrastructure for aeronautical purposes. There's many players that need to be playing the same song. Airlines, obviously. We also need regulators to be on board and synchronized. The communication service provider, the air navigation service provider, equipment, and also aircraft manufacturers. Those prominent players would need to have a common plan, a common understanding, and to move into the agreement of deployment of any future communication system. We're also looking at communication infrastructure that is scalable. Of course, the technology should be ready to support a well-managed global implementation, but also have the scalable nature so that you can deploy where and when needed rapidly. So that is something that we need to balance out about the need of global implementations, but also the capabilities to scale and moving forward with, maybe a cellular type of scalabilities of deployment. Also, one thing that actually with the discussion related to integrate CNS and some of the promising technologies coming forward, if there is any communication system that can also support other function, for example, navigation and surveillance function, of course, those options would be considered positively. But that would need to come with a very well-defined what is the primary and secondary role within CNS. And we do not want a system that lead to a single point of failure. integrated CNS function doesn't necessarily mean a single point of failure. If you decide right, if you put a well-defined primary and secondary role, and then that issue of putting all eggs in one basket can be mitigated. But of course, that requires a lot of careful consideration. So that covers pretty much all my key points from the airline's perspective of what are the key considerations for future communication infrastructure. So I think I send it back to you, Jackie, for the next speaker. Thank you.
Thank you very much, the panel, for this presentation on IATA perspective. We're having a lot of questions from the question chat and inline. So Philippe Sacré is answering to some of them, but we will take some of them later on. But don't worry, in the meantime, we will collect all the questions and answer in written form. Suggest we move on now to the next presentation from the SESAR joint undertaking. So this presentation will be given by Ruben Flor. So over the last 10 years, Ruben Flor has been an ATM expert with the SESAR joint undertaking. He's involved in ensuring the coherence and completeness of the SESAR research portfolio with a particular focus on high-level technical architecture, system-wide information management, SWIM, cybersecurity, and CNS. He built on early career in the flight planning system developed for KLM, and later in a system strategy developed for the Dutch air traffic control. So Ruben, the floor is yours.
Thank you very much, Jackie. Can you confirm you see my screen and you hear me?
I confirm we can see the screen and hear you well.
Good, thank you. Thanks everyone. Thanks also IATA and ICAO for setting the scene. And I feel a bit, so I'm telling up front that what I'm going to tell is maybe slightly, you'll feel it as a deja vu, because what is mentioned by, in particular, IATA as requirements is actually what we are building in SESAR. So, but it may feel a bit like a repetition, but you'll see that the difference is that we're actually going a bit more into the technical details. So regarding that, also telling you up front, Jackie mentioned it already, there will be another webinar at the 2nd of June, where we are actually inviting the technical experts who are building this system as well as the multi-link system to show how or explain in more technical detail. So for here, just providing an overview. So as a introduction, when I think of air-ground communication from an air traffic control perspective, I would see a controller talking to a pilot. But obviously that is not the only communication there is. There is also the AOC, or the Flight Operations Center, communicating with the pilot while flying, either directly to the pilot or through ACARS or through an EFB. And even that is still not the only thing. There is also the airframe itself, which can downlink data. So, for example, if we look at new concepts, we have the trajectory prediction from within the flight management system, which can be downlinked, like the EPP, Extended Projected Profile, one of the SESAR solutions. But you could also think of flight data or engine data that is transferred or necessary from an AOC perspective. Now, the new kid on the block is the drones, or that are related to U-Space, but we also have the RPAS, so remotely piloted aircraft, that are integrated into an IFR environment. So both here have also introduced a new need for air-ground communication. And that is still not the whole story. We also have the high-altitude platforms, the supersonic aircraft, the transition to, or the rockets that go to space. So there is more and more going on in the higher airspace, above the conventional air traffic control environment, which also requires air-ground communication in the future. Now, having said that, that is still not the only thing. First of all, it's about voice, but not only voice, it's also data. And I think what we'll see, and the next slide details that a bit more, is that there's a gradual transition from voice more and more towards data. Obviously, there's also just the passenger that communicates with the internet. But what is quite important is that we do not consider that within this scope. So from a air traffic control, or actually anyway, from an aeronautical point of view, there is a very tight, very clear segregation of passenger in-flight services versus aeronautical applications, which are safety critical and can be time critical depending on the application. So if we look in a bit more detail at the type of air-ground information exchanges and the evolution we see in there, that explains a bit why we are looking at new data links. So if you look today, the voice clearances are just done over broadcast RT, so VHF. There is a bit of data link, which is the CP2C, but it's relatively straightforward. It's relatively simple messages. So the climb descent clearances, the direct clearance, turns and headings, and the sector handover. From an AOC to an aircraft communication, we see actually there is gradually more and more communication, which is actually one of the causes of the VDL Mode 2 having a bandwidth problem, is the fact that it's shared with the AOC communication. If you look at what we're expecting tomorrow, is that we see a shift from the technical conflict management towards more pre-technical conflict management. So instead of having just direct clearances for the first next step, we're moving towards transition-based or trajectory-based operations. So that includes what I just mentioned before, the EBP downlink, or the Flight Management System Trajectory Prediction downlink. And to close the loop, we have from the controller back to the aircraft, the complex clearances. So basically not just saying the first next step for control, but giving a bit further ahead the plan of what the controller has in mind, all the way to resuming to its original trajectory intent. So having both the EVP downlink and the complex clearances together makes the control more a closed loop. And doing that a bit further ahead than just the technical clearances allows for much more fuel efficient and cost-effective flight management. It also includes trajectory negotiations, so not just issuing a clearance, but actually also negotiating, communicating with the pilots to see what is best for them in the context of air traffic control. We're also looking at a new concept, which is called flight-centric. So it's moving a bit away from sector control to sector-less control, which is more allocating controllers to, for example, specific flows. Then on top of that, what is becoming more and more relevant is aircraft as a sensor, so as a downlink of observations or sensor data from the aircraft. So I already mentioned that from an AOC perspective, but if we look, for example, a bit further ahead at what we see currently upcoming is the need to be much more environmental friendly in our aviation environment. So we also see that there's, for example, a need to avoid the production of contrails. So avoiding the production of contrails requires that we understand the humidity of what is in the air. So downlinking that humidity, so I saw somewhere, I think in the questions already, the Amdar mentioned. So downlinking humidity is one way to make sure that we can actually proactively avoid the production of contrails. Then from this, I think already mentioned in particular by Ayata, also by Akeo before, we see an increased traffic between AOC and aircraft, but also in direct support of airline, of the cockpit operations with more up-to-date and more fine granular charts, for example, from meteorological data and aeronautical data. And for those who want to have a more closer look at that, we also did quite some time ago the SWIM global demonstrations a few years ago that actually gave very good examples of what kind of data we are working on and what are actually currently being deployed in operations. So even though they may not be that time critical as air traffic control clearances, they are still safety critical. They have to be correct. And they have to be there, maybe not within seconds, but at least within minutes. And then the flight performance data downlink. And then, and as the last row here, the new entrants, which I mentioned, so the IFR integration of remote piloted aircraft, USpace or UTM, and the high altitude platforms. So why LDACS? So LDACS, first to explain, it is not in the VHF spectrum as we currently have our VDL Mode 2 and the VHF radios, but it's moving to a higher frequency, which is called the L band, because there is more space, and because there is more space for much more bandwidth. So we consider that an upcoming air-to-ground communication standard as one of our key components of the what we call FCI, Future Communications Infrastructure for Air-Ground Communication, which is not only the LDACS, which works terrestrial, but it works in a seamless integration with the airport data link, Aeromax, and the satellite communications when there is no Earth beneath the flight, for example, oceanic. So to keep in mind that when you're talking LDACS, we're both talking transmitter and receiver, so avionics and ground systems. And as already identified, we're not only looking at using it for data communication, but actually also for voice, and also for as a backup system for navigation and potentially surveillance. And one of the requirements, and so we are working on that, is that you have, contrary to what we currently have with VDL Mode 2, for example, or with ACARS before, is it can be secured. It is scalable and it is spectrum efficient. And one key aspect of being spectrum efficient is actually the fact that it can be combined with the alternative or the backup for navigation and surveillance by using exactly the same spectrum, the same frequencies. So it doesn't require more spectrum. So you basically, from a spectrum perspective, get the alternative navigation and surveillance for free. Obviously, the LDACS itself is not for free. So I thought some questions on the CBA. Maybe to highlight that, we are working on a integrated CBA for the whole future communications infrastructure. So including the multi-link with all the other links in there, which should be ready by the end of this year. If we zoom in a bit more on spectrum, so the current VHF does not have sufficient spectrum available, and not just to provide for the broadband, but also it would not work in the transition period. So we're looking at the L bands between 960 and 1164 megahertz, which means that it's going to be co-located with the DME in the L band. It is designed as a cellular system. I think that was already mentioned before by Vaughan. Obviously, it is still segregated from the in-flight entertainment services, which are out of scope. Now, here are some figures. I saw that also in the questions. People want to see figures. So what does it mean in terms of bandwidth? We're anticipating, but we're still validating at the moment, a 50 to 200 times higher throughput compared to VDL Mode 2. And the fact that it's scalable and cellular-based means that it allows for a stepwise deployment, which means it doesn't need to be a big bang all across the world or all across Europe, but we can actually gradually increase it on a need basis. And that also allows for a gradual transition from VDL Mode 2 to full LDACS. So from a safety and security perspective, so this is about quality of service. And that links actually back, so remember the word quality of service, I'll come back to that in the multi-link context. So if we look at security characteristics, we would think about availability, integrity, and confidentiality. And the main reason that LDACS is able to guarantee the availability for the safety and time-critical services is that it uses service priority. So there are different priorities of different messages. That way, the high priority messages will always prevail, while the lower priority messages are still going to be there as soon as there's some bandwidth available. So that makes it possible, unlike we have today with VDL Mode 2, to have a combination of ATC applications and AOC services at the same time, such that ATC always prevails for the time-critical applications, and yet AOC is served on the same data link. So on the integrity and the confidentiality, because of the higher bandwidth, I would say, and the fact that it's all IP based, it is very easy to introduce in this data link both authentication and encryption to ensure integrity and confidentiality. Now, what is essential in terms of interoperability is the compatibility with both existing and with future protocols. We don't want to throw away what is currently already working. So what it means is that as a requirement, and again, it's what we are validating at the moment, is that LDACS is compatible with ADSC, with the EPP downlink, with the current CPDLC applications, as well as with emerging ATS B3 services and the SWIM services that we mentioned before, for example, for the EFP. So also mentioned already before, I think, in terms of space constraints from an aircraft perspective, the avionics, so the radio that is being developed, will not require more space on board. So it can serve simultaneously LDACS and VDL. And also the antenna, a dual band VHF and L-band antenna has the same footprint as a current VHF antenna. So no new additional space requirements there. So this shows the multi-link. It's again the aircraft trajectory on top from departure, climb, cruise, descent, and landing. And you'll see here that there are various links, data links available. So on the ground, it would be more obvious to use already now high bandwidth, but there are less time critical applications, lots of less time critical applications running it. Well, actually, if you look at the in-flight phase, terrestrial, we could use LDACS and oceanic SATCOM, and we would want to have a seamless transition between all those data links. So for the in-flight safety critical services, I think I mentioned it actually quite somewhere before. I'll just show it here to emphasize a bit. So the requirements for in-flight safety critical is that it has the reliability, the quality of service has to be high. The robustness has to be high. It has to have good range, and the mobility requirement is there. So mobility is something which is quite important. It means that the aircraft are flying, so there's a Doppler effect because of the speed of the aircraft, and also they just continue switching from cell to cell. So, and that from a user perspective or a systems perspective, you should not see the transition from one cell to the next. So that's what we call mobility. So this is an architecture from the multi-link concept. So at the bottom, you see the different data links, and then the multi-link management manages the quality of service that are required by the different applications and chooses which one is the most cost-effective data link that is available. So already mentioned before, not only are we looking at data link and voice. Actually, I didn't know if I mentioned that particularly much, but I'll come back to that in a moment. So there was a lot of emphasis on data link, but actually, if we have an IP layer available with high bandwidth, you could actually also run digital voice over it. And we are investigating the possibilities, the feasibilities, and also the applicability of digital voice, in particular in the en route environment. But coming back to other applications, so also for APNT, so by using the ranging data, there was also a question I think I saw. So we currently have validation ongoing at TRL4 level to validate the accuracy of the ranging of the LDACS stations, or ranging against the LDACS stations to provide a way to get the position. And again, as said before, it is in particular driven by the fact that you get it from a spectrum perspective for free. So to give a bit of an overview of what has been done in terms of R&D and what is still ongoing, the data link applications, from a data link perspective, the first specification was already made in 2008, so that's quite some time ago. And it was followed by the first SESAR in 2011 to 2017, reaching TRL2 in Project 15. Then at the end of that, the ICAO standardization was started, and the LDACS SARPs were endorsed in October 2018. In 2019, we completed, meanwhile, it was SESAR 2020, the first wave, the TRL4 validation, and we're currently going towards TRL6. So that means not just the conceptual and technical proof of concept, but actually validating that in a real operational environment. Meanwhile, also currently ongoing, we're doing TRL4 validations on APNT to validate the accuracy of the APNT that we can achieve with LDACS. And we're also at the same time working on the TRL4 validation of digital voice. And there is a question mark on whether there is any need for further research on using it for alternative surveillance. You can imagine that it should be relatively straightforward. If you have it for APNT, you have the position on board, and you have a data link to downlink that position, then actually basically you have secondary surveillance. But we haven't yet looked into that. So summarizing, it's an L-band digital aeronautical communication system for air-ground terrestrial data link, required in particular for future operational needs. Although it's not just future operational needs, because actually, if you look at the capacity studies from VDL-2, you actually see that if you, for a moment, don't take COVID into account, the forecast was actually that in 2 or 3 years from now, the VDL-2 maximum capacity would have been reached, and we would not have been able to support any future traffic growth without looking at new applications that are currently being developed. So LDACS is scalable, it's broadband because it's operating in the L-band, it's integrated into the multi-link concept, it has a prioritization mechanism which allows for both safety critical purposes and for other aeronautical services. It includes authentication, encryption, and it is scalable, which allows for a seamless transition from VDL-2. It's swim ready. It enables air-ground digital voice with a potential reuse for APNT and surveillance. And that's it. Back to you, Jackie.
Thank you very much, Ruben. So still a lot of questions popping up. So suggest we move on as we are slightly late. We will go to the next presentation now that will be given by Brent Phillips. So Brent is a senior system engineer with FAA Next Gen organization and the US panel member of the ICAO communication panel. He's currently serving as the communication lead of the NAS Enterprise Architecture Roadmap team and leading Internet Protocol Suite standard developed for the FAA. Brent holds a Bachelor of Science degree in Engineering from the Virginia Polytechnic Institute and State University, and a Master in Engineering Management from George Washington University. So Brent is going to recall us a little bit the story of LDACS and what has been done a few years ago. Brent, the floor is yours.
All right, thanks, Jackie. Get this down here. Okay, thanks, Jackie. What I'd like to do today in this presentation is like to describe to you the FAA's involvement in LDACS up to this point and our intentions going forward. I think from the presentations that we've heard today, it's obvious that LDACS can meet the technical requirements for our future aviation needs. The question now will probably come down to more of a business issue, and I'll get to that in my last chart. So really, to give you an idea of what's been involved, and if you could advance the chart ribbon. Give you an idea of really where we started with this work. I'll have to take you back to 2001. At the 11th Air Navigation Conference, it became obvious that we were running into a spectrum saturation issue with our VDL systems. We needed to look at a broadband system in the future, and we needed to also look at converging on our technologies. Right then we were looking at VDL2, VDL3, VDL4, needed to really look at a common system going forward. So the ICAO directed the committee to go off and take a look at converging and coming forth with a common solution. So next view graph. So together, Eurocontrol and the FAA established the FutureCom infrastructure under the CCOM, which was under Action Plan 17. And from that, we described a number of activities that we wanted to achieve. One was we needed to establish the future requirements for communications. And we needed to investigate technologies that would support that, and in more of a flexible architecture configuration. We needed to develop a roadmap. We've done that, and I'll allude to that a little bit later on as well. We needed industry buy-in. Make sure that whatever we chose, that industry was behind us and they weren't going to step back as they did on VDL3 as we experienced in the US. And then finally, involvements in the maximum utilization of current spectrum. As we've noted throughout these presentations, spectrum is a major issue going forward. We're going to have to figure out how to use it most efficiently. So next view graph. All right, so we scoured the earth looking for a number of different technologies that would ultimately meet this need. And so we did everything we could as far as identifying all potential candidate systems, surveys, working with NASA. The Eurocontrol received an input from European manufacturers. From that, we identified 50 candidate systems that potentially could support our future requirements. Next view graph. So this next view graph will show you just some of those particular technologies. And what I highlighted was the ones that really came forth as the main systems that would have the best capability or the best chance of meeting all of our requirements. And I'll show you a chart later that describes basically the first system being more kind of in the US realm. That was a safety and service system that was already being used by our police and medical facilities here in the US. And then there was the BVHF system, which was more of a European consortium system that was being forwarded by Frequentis and other manufacturers. What I'd like to do here is just take a second and give you an idea of what's keeping me up at night. And I think it's a question that's really going to come down to whether LDACS is the right solution, or whether some other solution should be considered. And that's that and I'll ask Vaughn maybe to plug his ears for a minute here. The ICAO standardization process is much too long. I mean, you've seen with VDL2, that's taken 15 to maybe 20 years to actually get in place. We're still working on standardizing the applications. So what happens in that time frame is that the technologies are moving at a lightning speed, and they're overtaking this technologies that we had identified and that we were in the process of standardizing. So I'll give you an example. Aeromax was one of the systems that we actually identified for the surface communication system. It was already established. The IEEE standards for the WiMAX were already established. We said we can get these standards done in place. We're not going to run into anybody coming in and identifying new technology between now and the time we get this thing implemented. Well, 2 years into the time that we actually had been standardizing, everybody was asking, why aren't you going to LTE? And we were like, well, we needed to sit down and kind of huddle and decide, hey, we've been putting 2 years into this effort. Should we actually jump ship and switch to a new technology? And really what we came to agree on was the LTE chip manufacturers were not interested in moving to the 5G band to support our small production lots. The aviation community is very small compared to the cellular community. You're not going to find very many manufacturers who wanted to produce a one lot production for the aviation needs. Secondly, the WiMAX met our requirements. We were like, well, yes, the other system is newer. It might have a couple of extra bells and whistles, but WiMAX was doing what we needed it to do. And thirdly, is we can't keep chasing the next new technology. If we do that, then we're basically going to put in a number of years on a particular technology before we jump to the next one. We'll never come out with a solution. So really what I'm trying to do is make you aware that with LDACS, we have put in the time, we put in the effort to standardize this. Do we really want to take the time to jump to another technology that may meet our particular requirements, but at the same time, not provide that much more of a benefit? So let's go to the next view graph. All right, so as I mentioned before, we developed the COCR, that's Communications Operational Concept Requirements document. It described what we needed for our future system to do in order to support all of these new applications that were described in the earlier presentations. So that document was used as our basis for evaluating the technologies. Next view graph. Okay, so when we started looking, we realized, you know, all those candidate systems that we have, none of them would actually support all of the domains that we operate in, airport, oceanic, and continental. We did find that there were particular systems that were best suited for those domains. In other words, the WiMAX system, the satellite systems, oceanic. And then, as I mentioned, we came down to really 4 candidate technologies, which we were looking at further to down select. Now, I'll point out that you see the BVHF, that will be developed further into the BAMC. So there's a number of name changes throughout the technology development, but I just wanted to make you aware that that is the system that will ultimately lead us to the LDACS. Next chart, please. All right, so what was the recommendation coming out of the study? And that was that, yes, we're going to go ahead and support the BAMC system. And that's because, number one, the technology met our particular requirements, and we figured that if we can take the best attributes of that P34 system and blend them into the BAMC system, then we get the best of both worlds. The rationale going forward is that it was in the best interest of aviation. When we sat down, we could have fought this thing out for years between the US and Europe, but we've done that before, and we found out that that's not in the best interest of anybody. So what we did was we said, look, you guys have the immediate need. We're not as in much of a spectrum constraint. I don't think the US is going to put a lot of money to the technology at this point. Why don't you guys take the lead on the BAMC system, and we will support that activity. Okay, it's politically acceptable. That was basically the manufacturers bought into it, and the SESAR consortium was willing to put some funding behind it. And then finally, the Europeans, as I mentioned, had the more urgent need with your spectrum constraints. Let's move to the next view graph. All right, so as I mentioned, let's go ahead and take the best of all worlds. We folded in the benefits or the best technology attributes from P34 and the WiMAX, put them towards the BAMC, and that's where we arrived at the LDACS system. Next view graph. All right, so something that took place that was really significant was back, and I guess it was foresight that we went in 2007 into the work, and we requested that we be able to operate communications within the navigation band. So you can see there that we were given basically approval to operate the LDACS system once it's prepared in that band. That was quite a significant achievement. All right, so next view graph. All right, so I know it's kind of quick, but I think the message that I want to get across is that, okay, the down selection process was basically taking the best of all technologies, moving them into the designed LDACS system to support our future domestic operations. The FAA's future involvement, as I mentioned, we stepped back after a certain point. At about 2016, when the standards development started, we actually stepped back. We had been involved up to that point in the development of documents, including the transition assessment, the CONOPS, the LDACS architecture, the interference assessment, the specifications, a lot of activity that we were involved in. But at the standards point, we stepped back. I was a couple of reasons. Number one, we weren't sure if LDACS was the direction we wanted to go. We didn't have the immediate need. And I'll be honest with you, I think it was partly so because we didn't want to send the message to the VDL2 or the VDL2 community that we actually were looking at another system. They weren't ready to adopt another system right as we were now implementing VDL2. And it was a concern that if we did identify that we were doing that, they would say, well, let's hold off on VDL2 and we'll just wait for this new broadband system. So as a result, we were not involved in the standardization activities for the last three or 4 years. Okay, so given a determination on near to midterm, the FAA has not participated, as I mentioned, in the standards and validation work. Okay, so if you take anything away from this presentation, it's really the next 2 bullets. Okay, so the FAA has really changed its structure, its business case approach towards implementing and using aviation systems. We've gone to a service-provided structure, not only for the datacom, the ADS-B, the SWIM. That's going to be the future approach for the FAA going forward. In other words, we're not going to own, we're not going to deploy, we're not going to implement any future data link systems. And therefore, we would actually go and procure a service provider and let them select the particular technology that we would move forward with. And then finally, the last bullet is that the FAA's position is that when and if additional service is needed, it will consider the use of LDACS along with potentially other commercial available systems. Now that's kind of a real catcher there when you hear the word commercially available systems, because most of those systems are operating outside the protected spectrum. And that means that the FAA is going to look at systems that are commercially satellite systems, other terrestrial systems that could possibly do the job, but they aren't actually designed to operate in our protected spectrum. How would we get around that? Well, it's the performance-based approach that they're looking at. You may actually need additional systems in order to meet your availability and reliability requirements. But if you can meet the performance, then we don't care where the systems are. We just want to make sure that we get the best and the most timely. And also, if you go commercial, maybe you'll get those technology updates that you are seeing that take a longer time with the standardization process. Comes back, the last point, I guess, comes back though, do we then need to standardize these commercially available systems for aviation purposes? If so, then we might be back into the loop of looking at a 4 or 5 year time frame. And then we've gained little from that. So there's still some questions on the table, and that's really where the FAA is. Fortunately, we're not at the point where we need the LDACS system right now, but it will be considered when the other candidate systems. All right, thank you, Jackie.
Thank you very much, Brent. We are a bit late because we are almost at the end of the planned session. My suggestion is to conclude and to give the floor to Vaughan for the conclusion on the LDACS standardization. And then we can take a few questions before closing the session. Vaughan, on the last presentation on the standardization, are you ready?
Yes, I am, Jackie. Just give me a moment, please. I'll just share my screen. And Okay, hello again. I hope everyone can see my screen clearly. As Jackie mentioned, I'd like to just take a few moments to talk about the current status of the LDACS standardisation, and I'll preface that with a little bit of history, because that history is interesting. It involves industry as well as just ICAO and the other standards-making organisations. If we go back to the early days, or what I call the early days at least, in the mid-2000s, there was a joint activity between Eurocontrol and the FAA called Action Plan 17. Between them, they established something, and this is one mouthful of a title. They established a team that was called the Future Communication Study Operational Concepts and Requirements Study Team. Let's just call them Action Plan 17. Anyway, as mentioned, it was a joint FAA Eurocontrol activity, which was actually a very positive thing to see, because we're considering the needs of two important regions there in the development of these operational concepts and requirements. That group had two deliverables, something called the COCR, which was introduced by Brent just a few moments ago. The other deliverable was a set of candidate technologies identified for the future communications infrastructure, which you've heard about already today. Those deliverables were provided in the late 2000s, and a briefing on these was given to the ICAO Air Navigation Commission in 2009. At the same time, well, that work, though, was a result of a fair bit of industry involvement. There was a Eurocontrol contract given to DLR, Frequentis, the University of Salzburg, etc., to work on the LDACS design. They came up with a design in 2007 and an initial draft specification in 2008. Now, the specification itself's a great development, because that means we've got the tools with which to build these systems. That specification was subsequently revised in 2011 under the auspices of SESAR. Now, let's look at the current status. SESAR, who has support from Frequentis, DFS and DLR, the German air navigation service provider and the German Aviation Research Institute. They developed an LDACS Labs demonstrator in 2013. They also started performing L-band compatibility testing in 2014. And there was additional work done. The first serious LDACS Lab demonstrator was produced by another entity, DLR, in 2010. They also pursued the development of the LDACS ranging capability, which you've heard about already. And they flight tested this over 2011 to 2013. And I can say that the results were very successful and very promising. In fact, extremely good, in fact. So it was quite a pleasant surprise to see those results. And the robust receiver design, which was touched upon earlier, that was finalised in 2015. So you can see a lot's been happening, not just in the realm of the standards making bodies, ICAO and others, but also in industry as well. Now let's look at ICAO's role a little more closely. In December 14, at the first meeting of the Communications Panel, formerly known as the Aeronautical Communications Panel, a new work program item was proposed, and that was the selection and standardisation of the future terrestrial data link. There was also an action item to re-establish a former project team, the one that had actually worked on the selection of some of the candidate technologies, and they were to take this task to completion. They had their first meeting in 2016, and there's been a lot of joint work with the NAV Systems Panel and the Surveillance Panel on interference, as was mentioned by Ruben Floor earlier. The LDACS system sits adjacent to the spectrum used by DMEs. In fact, it's overlaid with the DME spectrum. So interference could have been a potential problem. It's been shown not to be a problem. However, more testing is needed, of course. And the other thing too is that earlier we mentioned that we have to use spectrum efficiently. If you can overlay two systems on the same band, I think that's a very efficient use of spectrum, and it's been shown to work. As well as that, the project team at ICAO is also working on the avionics architecture. There's a task force dealing with that, and they're going to look at some of these innovative ways of assisting the implementation of LDACS, as discussed earlier. The target for the group is to develop at ICAO SARPs and related provisions with applicability, which means that they're enforceable by November 2024, excuse me. So let's just look at some recent history. The ICAO Communications Panel set up the Terrestrial Data Link Project Team, PTT. They developed their initial standards in 2018. That is just a first draft, but a very substantially complete draft. They've been performing L-band and compatibility testing and frequency assignment work since then, and that's ongoing through 2021. And we expect to see the development of initial guidance material in 2022. In other words, the guidance material is there to basically help end users take the LDACS equipment, but install it and maintain it in such a manner that it does meet the performance requirements. Further developments outside of ICAO, we have SESAR 2020, which is doing some real pioneering work. They're looking at a refinement and extension of the LDACS specification with the inclusion of the ranging and navigation functionality. So that will be a formal part of the LDACS suite of capabilities. There'll be the finalisation of fully functional LDACS demonstrators, which are important. And there's also a German national project called MicroNav, with support from Rader and Schwartz, DLR, and a number of other industry participants. And their job is to implement a fully functional LDACS demonstrator and they've done that. And they've performed flight testing over March, April 2019. And again, I'm really happy to say that the results from that were really successful and promising. So with that, I'll end this part of the presentation and hand the floor back to you, Jackie. Thank you.
Thank you very much, Vaughan, for this, and to all the speakers for the nice presentation. I think we are a little bit late in terms of timing, so we will not have the time to answer to all the questions. But we receive a lot of very interesting questions that we will use to prepare the other seminars. And we have our colleague Philippe Sacré who is answering to some of the questions. But maybe just the time to take one or two questions. There is a question from the floor about the 5G. Why not using 5G technology, and why developing a new technology like LDACS? I don't know who can answer to these questions. Vaughan or Brent? Vaughan and Brent. Yes, Vaughan, please.
Okay, very quickly. Now, I think there are some obstacles that have to be overcome. We're looking at two different systems, and it's not to say that there's anything inherently wrong with the technology of 5G. It's got to do with the service delivery. 5G today is in the hands of the telephone companies. They provide a high volume product with very thin profit margins. Most of it, they would probably make, let me give an example, and I'm going to make this slightly humorous. I live in Montreal. Now, if a pop star like Justin Bieber was to land at Dorval Airport here in Montreal, that airport would be full of fans. And they'd be taking photographs of Justin Bieber, and they'd be taking selfies. The telephone company would make more money from that 1 hour, from the traffic from that 1 hour at the airport, carrying selfies and pictures of Justin Bieber or some other pop star, than they could possibly make out of aviation globally in an entire year. Having said that, are those companies likely to invest the millions, if not billions, to come up with networks that can provide 5 nines of availability, guaranteed low latency? With our cell phones, they drop out occasionally. If you can be in an area where the coverage is not so good, we can't do that with aviation. It's a safety critical service. If that hurdle could be overcome and we could get sufficient guarantees from the telco sector at an affordable price, and get real guarantees of service, Sure, it's a contender. It is a candidate, as Brent did say earlier, and we can't reject that. No, it would be a distinct possibility. But right now, I don't think the economics or the business case is that attractive for them. I may be wrong. Please consider. Thank you. Over to you, Jackie. Oh, Brent, sorry.
Thank you, Vaughan. Thank you, Vaughan. Brent, you wanted to complement that?
Well, yeah, I was going to say, I think Vaughan said pretty much exactly what I was going to, repeat, was that we're again looking at chasing a new technology. They're already talking about 6G. When we get to 5G, people will be complaining that we're not going to 6G. So the question is at what point, do we establish that this is where we're going as far as the technology, and we're going to, standardize on that. Again, back to the standardization process. Maybe Vaughan can address that. I know they're trying to speed it up. They said, well, they're going to go ahead and let standards activities be done in RTCA and EuroK and brought to ICAO. Well, that's not going to shorten the standards process. It's just going to be relocating the standards process. So, until we get that hammered out, it's going to be very difficult to stay up with the latest versions.
Mm-hmm. Yeah, if I just add one more thing too, sorry to barge in like that, Jackie, but one other thing that people haven't considered, and your comment, Brent, about the fact we've gone from 3G to 4G to 5G and 6G is bound to come, is true, but that's because the phones are disposable items. They're not designed to last 10 years. And every couple of years, the average user renews their plan. Part of that renewal includes a new phone, hopefully with new capability. The avionics in an aircraft generally stay with the aircraft for its lifetime, 25, possibly 30 years. Why? Because of the huge effort of integrating it into the aircraft, and also the huge effort that they have to undergo with certification. And that's one of the things you never hear anyone talk about, certification. Is the certification process going to keep up with each next generation of cell phone and so forth? I don't know. What I do know is what we're confronting today, and I do know that we've got solutions based on the problems that we face in aviation. If they can be solved by outside parties, great, they're candidates. But there are two big things we have to overcome, which I've just mentioned. Thank you, Jackie.
Thank you, Vaughan. Thank you, Brent. We have a lot of other questions on the technical capabilities of LDACS for the navigation purpose. My suggestion is to wait for the next webinar, because the answer will be given much more in details. The same on the technical matters. Maybe we can take quickly two other questions. A question on AOC versus ATS. I mean, do we have to have the same technology carrying on AOC and ATS? And I think Nopodol provides a clear answer already to that, but you may wish to come back a little bit of the AOC versus ATS traffic.
Yeah, Jackie, very, very good questions. Both are important. Okay, ATC is safety critical, it's time critical, so that message and the quality of service that accorded to that type of message need to have high priorities. No question about that. AOC is also operationally important, essential. A lot of airline operation cannot be conducted without that. Now, why we are looking at a common infrastructure or common system, I think the key point is the resource we have on board the aircraft is very limited. And historically speaking, the start of the use of data link, the share resources between AOC and ATC have been accorded quite appropriately. Now, with that said, I do agree that we have something that we can improve, that the capability of provide a proper prioritizations, and that is what need to be in the future communication system. ATC messages for ATC to provide air traffic control to provide the aircraft separation should have a very, very high priority compared to some other AOC messages. But to have appropriate prioritization scheme doesn't mean you need a separate system. That's the technical capability that should be introduced, and that's what we're looking for into the new operations. Yes.
Jackie.
Thank you. Thank you, Podol. I think it's important. I would like that we are taking a last question from the floor regarding the potential operation of LDACS for the U-Space. And maybe a question to Ruben, as you spoke about U-Space and UAVs. The question is, can LDACS be used for the let's say, for the drones, for the UAVs?
Okay, yeah. Well, before I go to the U-Space, I just wanted to make a little remark on the previous discussion about, in particular, to raise the issue of security. So I think if you look at commercial services or commercially available air-ground data links versus LDACS, and you look at availability requirements, I think there is already an issue there because the priority mechanism is not inherently implemented in commercially available systems. They would not prioritize ATC over customers that are paying a lot more. But if you look in particular at the reason that we're segregating commercial services, commercial in-flight from ATC or safety critical services, the fact that they are completely segregated. And I think that is something that is really important. So we actually do have some research looking into using commercial services and still meet the same quality of service requirements, both on security and on availability, latency, robustness, etc. But it's far from obvious. So that the research that we have on there, I would say, is more at the level of exploratory or fundamental research than it is at applied research or industrial research at the moment. So, but then coming back to your question on U-Space or drones, IFR integration of ARPAs, I think what is important to realize there is that the drones air-ground data link consists of two different aspects. So it's the C2, the command and control data link, and it is any communication that is ATC related. So in particular, if you look at the IFR integration of ARPAs, we are going to see some changes because the pilot is actually on the ground. So in fact, the ATC data link or the ATC link voice and data that we would conventionally have with a normal aircraft air-ground is now actually going ground-ground. But the air-ground is now from the ARPAS operator to the drone or to the ARPAS. Oh, but the impact of that is actually only over the C2. So the C2 at this moment is considered to be, if you look at all the manufacturing industry, to be going over commercially available data links. Now, whether that's going to stay that way, I would actually doubt, because in particular, if you look at IFR integration, that command and control becomes safety critical. So I can imagine that some of that may be transferred in the future to the safety critical applications or the safety critical, for example, LDACS. But at this moment in time, I think if we look at the needs that we have in general on UTM, U-Space, CNS, I think that's all still in progress. So there's work in progress, and if we look at the services that are being defined, a lot of that is still in terms of U-Space about segregated airspace, about having U-Space not being overloaded, about registration of drones, but actually going towards separation and integration of drones into an ATC environment. I think there's still a lot that needs to be researched before we have the actual requirements. We are looking into it, and we are open to it, and I think it is a good opportunity because I expect that we will have more bandwidth, but what exactly is needed, we don't know yet.
Okay, thank you very much, Ruben. Looking at the time, I'm afraid that we won't have to take much more questions. Maybe can we do a quick call the tab with the last word from the panel members, starting maybe with Vaughan?
Oh, yes, thanks. Well, look, I think this is a great opportunity today. It is a shame we didn't get to deal with all of the questions because I think a lot of them will be very thought-provoking. So with that, I'll look forward to the next webinar and a whole slew of more questions. Thank you.
Thank you, Ron. No, Podol?
Thank you, Jackie. Obviously, this is one of the very interesting webinar, and it's quite important because we're looking at a very important infrastructure, communication system for aeronautical purposes is probably one of the key fundamental infrastructure that's required for the future growth of ATM, air traffic management, trajectory-based operations, and so on, you name it. Newer operational concepts that are being thought of at this time, pretty much almost all of them would require a higher throughput, higher reliable communication infrastructure to support it. So, of course, we also have a lot of candidates that we need to look at, and all of them are still on the table. And this is why it's very important to have this conversation to discuss what are the key considerations and the key requirements so that we can understand before we actually have to make a decisions moving forward. The fundamental importance of the communication infrastructure, I think that is very clear by itself, and that time to make decision is coming soon. So the more we know and understand each of the consideration from all the stakeholders and all the system from the technical level as well is very important moving forward. So thanks Eurocontrol for arranging this event. Thank you.
Thank you, Nepodol. Brent?
I would just like to thank you, Jackie, for the invitation to speak today. It's obvious that the future comm infrastructure work that we did back 2006 is really mushroomed. Everybody in the U.S. is aware of the technologies that we've suggested, and I think that it was some good work, and I think we're still very close to making some of these realities. So just offer to keep working forward, moving forward.
Thank you, Brent. Ruben?
Thank you, Jackie. I think regarding in particular this webinar, what I really appreciate is that we're talking here with every one of us. So we have ICAO, IATA, the FAA, and SESAR all talking about the need to have a broadband terrestrial data link. And I think we touched upon the topic of performance-based. So what is clear is that we're moving away from just technology-based standards, regulations, SARPs, etc. We're moving more and more to performance-based. And actually, we have been discussing the performance requirements in terms of latency, bandwidth, etc. But what is still important, even when it's performance-based, is that we should not forget interoperability. And that is actually why we're here together with all of us, because in the end, we have ground, performance-based infrastructure, and we have avionics. And that avionics needs to work with wherever the aircraft is flying. And in the end, it is technology. So that's why I really appreciate that we're all here together discussing how to move forward on this.
Thank you very much, Ruben. And I think we are at the first webinar. So we initiated that from Europe with the Eurocontrol and the SGU. I mean, it doesn't prevent that for the next coming webinar, other regions of the world, if they wish to present what they are doing, that would be more than welcome, because we know that there are some developments that are going on. So I take this opportunity to remind you that the second webinar will take place the 2nd of June at 3 o'clock, same time as today. We expect to go much more in technical details, and it's something that will be driven by industry with a large participation of the research centers and laboratories, just to explain what the details on the technology for a better understanding on the way it works. I take this opportunity to thank all the panel members for their contributions. Thank you very much again for your contribution, your presentation, and for the debate we have had together. And I would like to thank also all the participants. I think it's almost 5 o'clock for a Friday afternoon, at least in Europe. We are almost close of business. I know that in the US and in Montreal, you have to continue a little bit, but you are not too far. So I take this opportunity to thank all of you, to wish you a nice weekend, and hope to see all of you at our next webinar on the 2nd of June. Thank you very much, everyone, and goodbye. And again, some question. We will provide through the SGU website a copy of the slide and the answer to all the other questions to which we didn't have the time to answer today.
Okay.
Thank you very much, everyone. Goodbye. A nice weekend.
Thank you very much.